Hey, good afternoon. So in September, we are pleased to have Professor Hui Zou from University of Minnesota to give the talk in our monthly webinar. Professor Zou received his PhD in statistics from Stanford in 2005, and then he became a full professor in 2014, just in 9 years. He is an expert in high-dimensional statistics, machine learning, data science in general, and has developed many influential methodologies, theories, and algorithms. Professor Zou has been the Web of Science highly cited researcher in mathematics from 2014 to 2019. And the R packages he developed by his group have been downloaded over 500,000 times and also used by multiple companies in industry. He's an elective fellow of IMS and ASA, and he is a recipient of many awards, including IMS Treaty Award, McKnight President Award, and NSF Career Award. Today, Professor Zou is giving a talk on sparse convoluted rank regression in high dimensions.
Thank you so much, Hui, for the kind invitation and very generous introduction. Yeah, today I will be talking about recent joint work with my former student, Li Zou, who just graduated and joined Hong Kong Baptist University as an assistant professor. And also my former student, Wang, made a lot of contributions to the computing part of the project. Yeah, so basically, the topic itself is about high-dimension regression, a very classical topic, and has received a lot of attention in the literature. So it's kind of difficult to imagine what else can we say about this very mature topic. And I hope that today's material can give you some new excitement. As we know that typical methodology are based on penalized squares for doing regression, especially high-dimensional regression. And I guess there are two reasons. So one reason is that historically, when we develop those high-dimensional techniques, we start with the least squares method, and we modify it, like lasso and scat and ElastNet and so on. And another important fact are simply based on theoretical convenience. So if we look at the theoretical literature on high-dimensional regression, you will find that the standard assumption is the following. So we assume that the data are actually generated from a linear regression model, has this kind of additive error form, and the error term is actually sub-Gaussian. And we assume sub-Gaussian for technical purpose because that's how we can handle so-called ultra-high dimensionality, in the sense that the logarithm of the number of covariates can only be a little bit smaller than the number of sample size. Technically speaking, if we switch sub-Gaussian error assumption to something like polynomial tail error distribution, then we cannot handle the ultra-high dimensionality. Well, so for some reason so let me first, before we present the methodology, let me show the simulation studies. I mean the real data applications to basically get your attention about this new methodology I'm going to introduce today. And sorry about this question mark in my reference. I don't know what happened. So we'll consider this kind of a well-studied red eye data set in the high-dimensional literature. Many researchers have used this data set to demonstrate the proposed methodology in their papers. So basically, we want to study how a retina disease-related gene is associated with other genes. And in the original data set, we have over 18,000 genes, and the sample size only 120. As a matter of fact, our methodology can handle all those 18,000 genes. a model fitting process without any difficulty, because we're going to show comparison with other methods, and other methods doesn't necessarily have the same kind of capacity. So we kind of reduce the dimension to either 300 or 5,000, so that other methods can also run relatively efficiently. And for the feature screening parts, we tend to use the model-free method called fused common mode filter. That basically give us more robust feature screening results in general. Should be better than something based on, for example, t-test or correlation screening. And we will repeat the whole process 200 times. We split data set into training set and test set, mostly because we do not know the truth, so we can only use prediction performance to objectively compare all those competitors. So here's the result we got. Suppose we reduce the dimension from 18,000 to 300. We tried the classical method, penalized least squares, and we're using the scatter penalty because this is known to be theoretically the optimal choice. We see the prediction error is about 1.03 and times about 2.5 seconds. And if we increase, we know that this scatter can handle really high dimension problem, no problem, right, at all. So in the case of 5,000 dimension, we only increase time to about 8.8 seconds, and the prediction error is slightly worse. And that's also kind of expected because another reason we want to do feature screening is to further improve the performance of the model. Okay, so computation consideration is only the one reason, it's not the all the reasons. So that's kind of expected. So if you look at rank regression, that's the method kind of motivate our study, and I will give an introduction about rank regression. Again, we will use the scatter penalty because this is the theoretically demonstrated to be the right choice. We see that rank regression can actually do better than least squares, and that actually agrees with the theoretical prediction. But computation time is considerably more, or it's almost 10 times more, and that's only for p equals 300. When p equals 5,000, the computation time is 60 times more than least squares. Still can be managed with 500 seconds. That's roughly 8 minutes. That's just for one run, right? And so if you look at the new method, so CRR, again, for fair comparison, we will be using the same kind of penalty function. So the difference will not due to the choice of penalty function. We can see that we can even further reduce the prediction error by the rank regression. Okay, at least statistically speaking, the reduction is clearly significant. And if you look at p equals 5,000 dimension case, we find our computation time, just like least squares, quite manageable. Okay, use about 8 seconds, we can get computation done. And as I mentioned earlier, for our method, if you do not want to, if you feel uncomfortable using the feature screening method, we can directly use the original 18,900 some genes in the model and do the prediction directly. So I hope that this quick demonstration will earn your interest in the following part of the material. Okay, so clearly, as you can see, that our focus will be on the efficiency of the method. And this is also well known, even in the textbook examples about regression. So when data is heavy-tailed or have other type of non-normality, the efficiency of least squares may not be the best one. Okay. And many other alternatives have been proposed. For example, some famous choice include the quantile regression. Okay, it's often used a very more robust alternative least squares. But also we know that one possible drawback of quantile regression is that the efficiency improvement cannot be guaranteed. And for certain distributions,
when you switch from least squares to quantile regression, you may actually end up with losing a lot of efficiency. So as a remedy, the composite quantile regression actually fixed this particular problem of quantile regression by mixing several quantiles together. And turns out, the efficiency gain can be substantial. And more importantly, in the worst case scenario, there will be a lower bound for the potential efficiency loss against least squares. And for that same purpose, we can use rank regression instead of composite quantile regression. Okay, and rank regression, again, as I mentioned, I don't know what happened to the reference, and just isn't displayed correctly. The canonical rank regression, for example, here the reference would be the book by Hattensperger and McKean, the robust non-parametric statistics models. So in that book, they give a very clear introduction about this classical method. It's known to be very efficient, and also, more importantly, have an efficiency guarantee against any kind of arbitrary error distribution. And for computation purpose, sometimes we often use the second definition. The two definitions are actually equivalent in terms of how to estimate, how to compute the data. The equivalent form clearly looks more familiar and more friendly, because intuitively speaking, we can actually formulate a working data set and turn this equivalent form into a median regression, right? Least absolute value regression problem. So that's become something that much more familiar. But of course, this is not a recommended solution. That will only conceptually, is how we can understand this equivalent form. So penalized rank regression, of course, is a very straightforward extension of penalized least squares. We can use the equivalent form, right? Here we take the basically pairwise comparison of the residuals, then add the penalty form. And for the low dimensional setting, this was studied by Professor Wang and Li in their biometrics paper, 2008. And more recently, the high dimension theory, again, were developed by Professor Wang and Professor Li and their co-authors in the JASA discussion paper. So quick remarks about why rank regression should be considered seriously. First of all, for normal error, we know that has very good relative efficiency against least squares. And for heavy tailed errors, usually has much better efficiency. And even without assuming anything about error distribution, the relative efficiency of the rank regression with respect to least squares is at least 86.4%. Right? So that has certain guarantee, okay? And that's a property that cannot be shared by quantile regression, for example. And in their the more recent high-dimensional rank regression paper, additional theoretical property were established. For example, if we use a Li Zou penalty, we can see that the tuning-free property will give a theoretically chosen tuning parameter. So in some sense, this property can allow us to cut down computation time considerably, because usually in Li Zou regression, for example, nowadays, if you run Li Zou regression, I guess most people will use the GLMAT package, and the built-in cross-validation function is used to choose the Li Zou parameter. And suppose we do not want to use Li Zou penalty and use a scatter penalty, and then Professor Wang and Li and their courses established this oracle property for the procedure. And if you're familiar with the high-dimension literature, you know that oracle property is actually the kind of golden standard for establishing the optimality of a certain high-dimensional method. Right. So those are good things, and all those are the reasons that we should be using rank regression. But of course, there are also challenges. Okay, and the most important challenge is that the high-dimensional rank regression can be difficult to use in practice, precisely because of computational issues. As we have seen in the red eye example, when the P, which is the dimension of the covariance, is about 5,000. And by today's standard, 5,000 is not really very challenging, like high dimensionality. Comparing to these squares, right? You take like 60 more times to fit the model. So that's one issue. Second issue that people may wonder that why not use some kind of computation trick to boost up the computation? For instance, the least squares, penalized least squares, is made super efficient by using quantity descent, thanks to Friedman, Hasty, and Tiptroni's GMNet package. Why can't we do the same thing? Well, the answer is, in theory, we cannot do that. And we should not do that, because this will be the wrong algorithm to apply. More precisely, the reason comes from the fact that rank regression use a non-smooth objective function. Even though when a penalty could be L1 penalty, for this type of problem in general, we should avoid using quantity descent, because quantity descent could give you the wrong solution. Actually, in the textbook, not textbook, in the research monograph, I co-authored. I have the honor to co-author the book with Professor J.T. Fan, Li, and Hui Zou. We had a chapter about rank regression and quantity regression and so on. So we actually use a counterexample there to show that for non-smooth objective plus L1 penalty, quantity descent actually will give you a solution that is obviously the wrong solution. Okay. So that should be avoided actually. And therefore, what do we know by now is that the standard correct algorithms should be linear programming by its interior point method. This is correct. However, this type of algorithm will not be suitable for large-scale problems. So I personally, had this kind of experience when we try to boost up the computation of quantity regression for really high dimension problems. The interior point algorithm really is very slow, although it gives the correct solution. So as alternative, prior paper we propose some kind of a different algorithm to make sure high dimensional quantity regression can be computed very efficiently. So having thought about all those issues, on one end, we really want to use rank regression because it's really nice, theoretically speaking. On the other hand, the computational challenge is there and it's not easy to remove. Can be removed, but it's not easy. So the big picture of our work is basically this question. So can we invent something new that has all the essential statistical property of sparse rank regression, but at the same time enjoys the computation efficiency of penalized least squares? And of course, the answer to this question by now, you can guess, is yes. And also we have demonstrated by using the red eye data example. But here we want to emphasize that also in the title of the method, we also mentioned it's kind of rank regression, but we are not seeking an approximate solution to the rank regression. Okay. So we will try to explain this point as we move forward. So now let's talk about the methodology we'll be talking about today. Let's look how we think about this problem. Okay, as I said, we are not seeking for a computational approximate solution to rank regression. We actually look at this problem from a new angle. So equation 1, that's the objective function in the rank regression. As we said, we're basically looking at the pairwise difference of the residuals. So if you look at the pairwise difference, and we can call it theta ij, what we can say is that the expression 1 looks like some kind of empirical average. Okay. So as in many other related models, when we look at the objective function, when we think about why this objective makes sense, is by studying its population version. Okay. We have done that repeatedly for many machine learning algorithms.
For example, the most famous one in the textbook will be the SVM. That's basically by looking at this, the population version of the SVM definition, people can make a statistical theory for the SVM. So basically, we're doing the same thing here and look at what is the population version of this quantity, and we realize basically it's kind of integral, some kind of statistical calculation. And here the capital F will be the cumulative distribution function of the pairwise integers. Well, and how do we relate the equation 1 to this population quantity? Well, imagine that you start with the population quantity, and because we do not know what is the distribution of the pairwise difference of the residuals, and we plug in the estimated version, like empirical CDF in some sense. So if you use the usual definition of the empirical CDF, like this, basically the histogram type, well, you end up with 1. Okay, so the connection between these two approaches is established through this kind of plug-in view. Well, since you are plugging an estimator, we may end up with a different expression if we use a different plugin. So suppose you use a different plugin, right? So we do not use this type of empirical CDF. Instead, use other kind of maybe a smoother one, and then we can find what is the corresponding counterpart of my integral. So that's basically motivates the calculation. And since we're talking about some kind of estimator of the distribution, so instead of using the empirical measure, you can look at the kind of smoother version, okay? Kind of like what we did in the kernel density estimator. So take a usual kernel function and kind of smooth it. So that's how we can consider the plug-in principle. We're going to plug in this F tilde into the population expression, and we want to see what kind of actual result we can get. And here we want to use these slides to comment on the choice of the kernel function. Now, first of all, K will be something that is our choice. So it's not really a tuning parameter per se. The usual choice of kernel function is satisfied with these of the theoretical conditions here. For example, we typically try to use kernel function like, if you want to try something with finite support, we try the Nichkov kernel. Something that with infinite support would be the Gaussian kernel. Now, in this, really, theoretically speaking, if you look at the theory, the choice of kernel really is not that crucial. Okay. So given any particular choice of kernel function, so we can do the actual integration and then find out again, the end result will be some kind of empirical average. But now this time it's not average of pairwise difference. It's a pairwise difference act on some new function we call LH. We use LH means that this is some kind of new loss function that depends on H. And H, you can interpret H as a so-called smoothing parameter as usual. Okay, it will be a positive number. And the analytic expression for this LH is given in the first bullet point here. Hope you can see my hand, the like symbol to the mouse. One way to look at this as an interpretation is that this is the convolution between the previous pairwise difference and now the kernel function. Okay, and therefore we call this objectively convoluted rank regression objective function. Okay, just by this kind of a expression. That's how we look at it. So what is advantage of using this, right? And for the rest of the talk, just for illustration purpose, we focus on this Nichkov kernel because, as I said, theoretically speaking, it really doesn't play such heavy influence on our final results. And so if you choose this simple kernel with finite support, sometimes computation becomes also relatively convenient. Then the expression of the actual loss function we introduced was given here. It's not very intuitive look at because we have mu to the fourth power term. So anyway, that's what we get, and that's how we use it to develop the next step. I just want to mention that, again, apologize for the question on my slide, don't know what happened. The smoothing a non-differential problem where convolution actually is not a new idea, okay? So we don't claim a lot of credit for it. If you look at the optimization community, even back in the 1970s, people use this to actually study the stochastic descent type algorithm. Okay, so they have considered this precisely the same technique. And more recently, in statistical literature, there's a paper in JBES by Fernandez. They studied smooth quantum regression. They used precisely the same idea for quantum regression, but they smoothed it. And they actually, I think the motivation actually to study what is kind of the theoretical consequence by using this kind of smoothing, quite interesting. And I think there's a high-dimensional concave regression by smoothing, recently JASA by Kim Tan and Hui Zou and Professor Wang, I think. So basically, study high-dimensional quantum regression by using smoothing. That what could happen. Okay. So now we see what is new in the quantum regression. Okay. It turns out we do end up some new methods that is not necessarily holds for the quantum regression context. So let's first examine the impact of using convolution. And so for that, let's consider the classical setup. Okay, the data from the linear regression model, and you have added the error form, and each one is independent of x. And one thing about rank regression that is also well known is that if you take the population version of the objective function and try to minimize it over beta, you actually end up with the true beta. Okay, so of course that's a wonderful property. That means in principle, you can exactly recover the truth. So here's a statement we can make about the smooth rank regression. At this moment, we are not talking about adding the penalty yet. If you do a smoothing, you use some bandwidth, h, like h equals 1, for example. Then we said you have a corresponding population version. Okay, so if you minimize it, as we did for the rank regression, we happily find that you also find the truth exactly. Okay, so I'm using beta h as a definition because if you just look at this problem, you expect that the solution may depend on the choice of h. But as a matter of fact, the solution actually is independent of choice of h. Right, so we have this kind of completely bias-free. In contrast, in the context of quantum regression, that's not the case. Okay, if you do quantum regression to some kind of smoothing of the population sense, the population minimizer will depend on h. The bias is there and need to be handled carefully. So that's one thing. For rank regression, we have this pretty neat unbiased, exact unbiased property. So let's look at what is the efficiency property of the actual estimator. So this is convoluted rank regression, again, without any penalty. And we studied the usual asymptotic property of this estimator when n goes to infinity. So we can actually derive the asymptotic normality of this estimator. And with this kind of explicit expression for the covariance matrix. Okay, but of course, this is not a very simple expression. So that's another nice thing we can say about the method. That means you choose any h, h doesn't need to be very small, any h like 1, you get this nice asymptotic normality. And of course, then we want to see, well, how good is this, right? We want to compute relative efficiency. And more interesting, we want to compare it against rank regression. Okay. So we know the rank regression have this asymptotic efficiency on top of the, that's the top line here. And that's, as I said, the book by Hettensberger and McKean, provides this precisely. Also in the in some papers like rank regression paper 2009, I think this also was given there. And so what we can do is take the ratio and calculating the asymptotic relative efficiency between the convoluted rank regression with hat H and rank regression. So we end up with some expression quite complicated. Of course, will depend heavily on the choice of error distribution. Well, at least the expression suggests so, right? So we did small calculations. First of all, we want to calculate what happens when H is small, because intuitively speaking, when you choose a very small bandwidth, our new density estimator becomes closer and closer like a histogram type empirical CDF. Okay, so you can imagine, well, the convoluted rank regression estimator is basically just like rank regression. So our expectation is that when H goes to 0, this relative efficiency will be 1. But we want to give more precise, quantification of this kind of statement. So it turns out we can make something even stronger. So if you do a small expansion of the relative asymptotic relative efficiency around 0, so H is small, what we find is that locally behavior will be the asymptotic relative efficiency as a function H is equal to 1 plus a constant times H squared. We actually can show that this is the case. Okay, so the first derivative is actually 0, it's gone. Of course, this probably won't mean too much if this constant is a huge constant. Okay, turns out we can do some kind of example by example evaluation, see how bad this constant can be. Again, we focus on this empirical kernel. In our simulating studies later on, we start kind of 3 type distributions. Of course, we can always study more, but I think that the message is kind of coherent, so 3 probably is enough. So we calculate the constants, basically the second derivative here, right? So sometimes the derivative is positive, sometimes it's negative. But in all cases, this, if you take the absolute value, is really a small number. So numerical speaking, really, if you look at relative efficiency when H is not big, like for example, if we put H small, okay, of course, it's just theory. We don't know whether H equals 1 is already small enough for applying that result. But at least the message is the following, right? The relative efficiency is pretty much close to 1 for practical purpose. Okay. So of course, this is a asymptotic study when N is very big, and H should be reasonably small, such that you can apply the kind of Taylor expansion results. So now we focus on impact on computation. So just give you a recall about the expression of the LH function in theory. So it turns out once we use a kind of a smooth kernel, at least you can take its first derivative, and first derivative is always ellipsis continuous, as long as the kernel we're choosing has a absolute upper bound, and usually this can be guaranteed because we have the choice to choose the right kind of kernel. So basically, this quick calculation verifies so-called quadratic majorization condition. Okay, and that condition is basically the foundation for using the generalized coordinate descent type algorithm that was proposed in a paper by Yang and Zou, 2013. Okay. So basically now, the rest is just implement the procedure, but now we know we can have very efficient algorithm to compute the high dimension convoluted rank regression with any kind of tool that of the usual form, like Lasso or SCAT or MCP. Okay, so that's also great news. So the conclusion is that by doing convolution, we theoretically end up something interesting, and computationally make this much easier to compute. So now, to really handle the high dimension case, we understand that a penalty function is necessary. So we add the penalty function. So in this class, in this work, okay, we want to study both lasso and the scat, just like the rank regression paper did. Again, we also need to assume the theoretical setup in order to present the theoretical results. And those are all quite standard assumptions. The only thing I want to mention is that because we want to compare rank regression in terms of variable selection result and so on, and since we're talking about variable selection, it's best to assume that you have so-called hard sparsity assumption. But if you do not care about variable selection precisely, you only pay attention about prediction of the model, we can easily replace the hard type sparsity assumption to the so-called soft sparsity assumption. That is, the true beta star, the LQ norm is in a kind of small hole, and that's basically all we need. All right, so as I mentioned in this class, in this talk, we can consider both lasso penalty and the scat penalty. Just presented the formal penalty here in case some in the audience have not used them. There's a well mature choice in the literature, and nothing more we can comment on. So let me quickly mention computation. As I mentioned in the 2 slides ago, it's like we have verified quadratic majorization condition. So in principle, we can apply the generalized coordinate descent algorithm, and it's guaranteed to give you the right solution and also very efficiently. But when we have a non-convex penalty, usually the recommended solution will be applying the so-called LLA algorithm multiple times. And in each LLA algorithm, we'll be dealing with kind of convex problem instead of non-convex problem. Okay. It's not recommended to apply coordinate descent directly with a convex penalty, non-convex penalty, because often than not, we will end up with something that is suboptimal. Okay. The LLA type algorithm has theoretical guarantee, as established in several papers in the literature already. So that basically means that eventually we just need to focus on how to solve this kind of convex penalty type convoluted rank regression. As I mentioned, the algorithm we'll be using is generalized coordinate descent because the objective function meets the quadratic majorization condition. And so the details of the generalized coordinate descent is that it's actually a mix of majorization, minimization, and coordinate descent. So combine both ideas together, that's how we guarantee you always get the correct and efficient algorithm. So for the theoretical purpose, of course, we always need to add assumptions, the so-called regulatory conditions. So here, this is some kind of regulatory condition for the error distribution. So it's not completely distribution free. It's like, can be any distribution. It still requires certain regular kind of normal behavior of the error distribution, but we do not oppose any strong, like tail behavior distribution on assumptions, something like that. Okay. So that assumption is quite weak in our view. And also design matrix plays an important role in any high dimensional models. So here is basically the usual type of assumption for, even for penalized least squares, we should also have similar conditions. And here, notice that we assume that there's an absolute upper bound for the value of the covariance. Because this is assumption used in the rank regression paper for establishing the tuning-free property. So we want to assume the same condition, and we want to show that the tuning-free property can also be established for this new method. So look at rank regression with penalty from lasso side. You have lasso penalty, we call it lambda 0. We add 0 here because turns out lambda 0 is something that we can, theoretically speaking, can pre-decide once you see the data set. Okay. So precisely speaking, lambda 0 could be a constant times the square root of log P over n. And the constant can be determined by looking at the largest possible absolute value of your covariance. Okay, as defined earlier, that big N. So lambda 0 is something that in principle can be pre-computed, as it's free of the true model. So on the usual dimensionality assumptions, as of is small compared to N, we can prove that the convoluted rank regression estimator has the same kind of rate convergence as the rank regression. Of course, the constants in front of the rates may be different. Okay, but that's the message. And the only assumption for H is that H should be bounded. You could not choose H like diverge. And of course, intuitively speaking, we should not use H that is huge. So that should be not a concern at all. So that's the first result. Just like rank regression, we maintain the tuning-free property. So now let's move to the scatter penalty. Now for scatter penalty, the rank regression is shown to be strongly oracle property, right? This is like the theoretically speaking, the best we can do. So for that, we have to define the oracle estimator. So now our oracle estimator, of course, because we are using the convoluted rank regression, so our oracle estimator should be based on the convoluted rank regression loss function. So here's a definition. We first assume you know the true subset of variables. And given that, you can estimate the beta star. And we assume that that is the gold standard. Because in reality, you never know what is A. And actually finding A is the most challenging part in high dimensional regression. So now you have actual estimator beta star with a tuning problem lambda. So what we can show is that if you look at the oracle estimator, you can have the usual rate, that's the kind of expected rate, square root S over N, well as the true dimension of the model. So as long as S is small compared to N, you have a consistent estimator when you look at oracle estimator. Okay. Previously, we have the asymptotic normality established for the oracle estimator when S is kind of fixed. Okay. In theorem 5, S is not necessarily fixed. And so we have the optimal rate, but thus far, we don't have the asymptotic normality yet. Now for the oracle property, so what we want to show is that our estimator is going to be just like oracle estimator, okay? Of course, under regularity conditions. And unlike the lasso, well, we can actually pre-specify the tuning parameter. For the scat, we have to say that your parameter lambda must be properly chosen, okay? And for the sake of presentation, I can use the messy formula here. And of course, H should not be too small in our theory, okay? So H cannot be really goes to 0 super fast. But as I said, usually if suppose in practice use H equals 1, so definitely 1 is bigger than square root of S over N over P. Then the LA algorithm that we've suggested, right? We suggest that should be the right algorithm for computing the scatter penalty convoluted regression. If you start with the lasso penalty, okay, so the theory says you compute lasso first. Lasso is tuning free, and then use lasso to initialize the LA algorithm. So you run the LA algorithm like 2 times. You can stop because theoretically speaking, you already got the oracle estimated. So this is called a strong oracle property. And of course, the choice of tuning parameter is always a headache in practice. Okay. Luckily, we can always do cross-validation as long as the computation of the algorithm is very efficient. That's from a practical purpose, not our concern. But theoretically, it's always interesting to see whether you have a shortcut, right, to reduce your computation even further. And we studied this so-called high-dimension BIC type criterion for selecting tuning parameter. The idea is the following, right? So we consider a list of lambda values. For each lambda, we can compute the estimator. So like we build up the solution path. And then along the solution path, for each choice of lambda, we calculate this called HBIC score. It's basically take logarithm of the objective function plus penalty imposed on the size of your fitted kernel model. Okay, and so this can be easily computed because beta star hat is assumed to be already computed, so you can actually also find the size of the model. And Cn will be a constant, depends on the sample size. For example, Cn will be log n as the usual choice. So what we can prove is that suppose you use that to choose your lambda, and of course we have regularity conditions. But if that's the case, you can actually use your BIC to pick the right model. And your selection will be guaranteed to be consistent because the selected model will be the true model. Okay. And therefore, this offers an even further reduction in computation because if you run 5-fold approximation, at least you need to run the whole procedure 5 times. But in using the BIC, you only need to run the whole procedure once, and then you can stop. So now let me use a remaining few minutes to basically give you some simulation demonstration to confirm the theoretical findings we have, right? So again, we consider 3 methods, and you all use scatter penalty to eliminate the impact of the possibly due to the difference, possibly due to the different choice of penalty function. And all methods are tuned by the corresponding high dimension BIC criterion. And in the simulation study, the dimension can be 400 or 3000. And we consider 3 types of error distributions, normal, and the other are 2 kind of non-normal distributions. One can be interpreted as contaminated normal. You have some kind of 5% outlier in the data set, and the other one is a heavy tail distribution, basically from T distribution is 4 degrees freedom, and we consider 2 types of correlation structure. It can be compound symmetry or autoregressive, and we use the usual those measures to compare estimators. Now, so what we see is that if you look at the normal distribution, the expectation that this squares is good enough. Okay, so no need to consider any other alternative. Indeed, that's what we see. Okay, but the message is that if you consider convoluted rank regression, we are pretty much close to least squares. Okay, sometimes you see the numerical number is a little bit better. I think that's just due to the fact that we have n equals 100. Okay, n equals 100. I think yes. So it's basically the small sample size property. And when people 3,000, we find the rank regression somehow the performance become notably worse than least squares, which is not so obvious when p is 400. Okay, that's the observation. Then if we switch the contaminated normal distribution, we notice actually the rank regression overall is really the best winner, the best performer, and least squares, as expected, are not going to perform well at all. But the importance is that the convoluted rank regression, the rank regression basically behave again pretty close to each other. Right? So when rank regression is the winner, the convoluted rank regression is basically very close. It's virtually a tie. And for this heavy tail T distribution, T with 4 degrees freedom, we notice again, least squares are not going to be the right choice. Well, we expect a lot of sufficiency loss. So if we switch to rank regression, we see the gain. The gain is also very substantial. But if we further switch to convoluted rank regression, actually we see even more reduction. Okay. So I think hopefully to show you that, as I mentioned, convoluted rank regression should not be considered as a computational kind of shortcut for rank regression. The two are actually different methodology. Also, they share a lot of similarity as well. Okay, quickly, let me draw conclusion. My time is up. So message is the following, right? So we know least squares is a dominating methodology in high dimensional regression, especially when people are doing real data analysis. But we should be aware that it has fundamental flaws, and we should care about this. And therefore, the rank regression is really a nice alternative. Okay, But because the computation is kind of difficult, and that motivated us to consider the sparse convoluted regression. And we have also showed that convoluted regression itself should be considered as a new methodology because it has different kind of theoretical property and empirical performance as opposed to the regular regression. And good news is this new methodology is actually ready to be used for large scale applications. We have the package available. And here's a piece of reference. Now you can see the missing reference from my slides. And again, I apologize for the question marks. And I think I should end here and answer some questions you might have. Thank you so much for your attention.
Okay, thank you very much, Dr. Zhou. And let me stop recording and we will move to the Q&A session.